everyone, welcome to another Math152 video lecture. Today you've got me, Jessica Stockdale, taking you through section 11.4 on the comparison test. So in the last class you heard from Brenda, who taught us about the integral test, which was a method to make it easier to think about sums of series by comparing them to easier to calculate integrals. And today we're going to carry on a similar theme, but instead of comparing series to integrals, we're going to compare series to easier to work with series. So it's kind of carrying on that same theme, but one thing you might have noticed is that when we're doing the integral test, actually we have to work out the full value of an integral when we often don't really care about the answer to it. Often we might just care about whether our series converges or not, and so doing the integral can kind of be a bit of a tricky extra step, particularly if we end up with an integral which is really difficult to calculate, or indeed you can imagine we might have situations where the integral was itself impossible to calculate. And in those situations, that's when our comparison test can come in really useful. So here, rather than trying to work out the sum of a kind of complicated series, we can compare it to an easier to work with series and use that to draw conclusions about the series in question. So we'll see a little bit more of the full details in a minute, but as always, I kind of want to motivate this with a bit of an example. So here we're going to think about the series here, the sum from n equals 1 up to infinity of 1 over n to the 4 plus e to the n. And we're essentially trying to work out here, as it says, if this series is convergent or not. So my advice in these kind of series and sequences questions, as always, is to write out a couple of the terms in the series first, just to see what it looks like. So here you can imagine as n increases, our terms are going to look like 1 over 1 plus e plus 1 over, 2 to the 4, so 16 plus e squared plus 1 over 3 to the 4, which is 81, plus e cubed, and so on. So my first my second step in these convergence questions with the comparison test is always going to be to take a bit of a guess. Do I think my series converges or do I not? And in this case, I think yes, my series probably is going to converge. The reason I say this is that if I look at the limit as n tends to infinity of my terms, 1 over n to the 4 plus e to the n, I can see that my denominator there is going to go to infinity, and so my whole fraction is going to have limit 0. So I know that the terms in my sequence go to 0, so my kind of best guess at this point is that the sequence is going to converge. However, we do know that it's not necessarily going to. So for example, we had our harmonic series in the previous 2 lectures, and we saw there that the terms did have limit 0, but indeed the sequence didn't converge. So we can't be completely confident at this point, but at least there's kind of suggestion that because these terms go to 0, the sequence is going to converge. The other thing I want to note here is that this series that we've got, the sum from n equals 1 up to infinity of our 1 over n to the 4 plus e to the n is not geometric. It doesn't fit into that nice framework for geometric series that we had before. You can note that because there's no constant kind of multiplier, no common ratio between the different terms in our series. And it's also not any other we could say well-known series. It's not exactly like a harmonic series, it's not one of our p series, so at the moment we're not really too sure what to do about it. But what the comparison test does, and we'll define this more fully in a second, but often we're going to want to compare more complicated series like this with those easy to work with series, all these kind of famous series that we know results about the limit of. So in particular, I'm going to say often we will compare with, e.g., our p series that we saw in the last class, given by the sum from n equals 1 up to infinity of 1 over n to the p. Or indeed our geometric series which we know are defined as the sum from n equals 1 up to infinity of a r to the n minus 1. And in particular, the reason, as I said, that we want to compare with these is that we know results about when these converge. So in particular, we know that our p series converges for p greater than 1. And we know that our geometric series converges when the absolute value of r is less than 1. And to see what I mean by comparing, we can kind of define over the page here. We can look at this section in the purple box. Here we define the full comparison test. So what I want to assume is that we've got two series, the sum of an and the sum of bn, and they're both infinite series. And we're concerned with finding out the sum of one of them. And what the comparison test tells us is that as long as we satisfy these two requirements that are given by these inequalities here, the two requirements in particular being that both of our sequences, an and bn, are positive. And the second requirement being that an, as it says here, must be strictly less than bn. And the important thing is that this must hold for all n. So we need those two requirements, and if we have those, and when those hold true, we can do this full comparison test. So this tells us, and there's two kind of different options for this. Let's say that we know our bn, that's one of our kind of famous sequences, our geometric series, say, but we don't know an. An is the thing we want to work out convergence for. Then if I've defined my an and bn such that these criteria here are satisfied, then I can say that if bn is convergent, an must be convergent also. So that's kind of saying I figure out something about my bn, and that tells me something about the an that I actually care about. That's kind of this first case here. The second case tells us it's kind of the other way around. Now we're going to assume that we know something about our an. It's a sequence we kind of already know about, and we know that it diverges. Then again, if we satisfy these criteria that we had at the beginning, the positive and the an less than bn, then we know that bn must be divergent also. And there's a couple of ways we can think about why this might be true. The first one is that we can notice that this is just like the comparison theorem for improper integrals. You'll notice that it's exactly the same, particularly you could have a look back at that section if you wanted to. Just like the comparison theorem for improper integrals, and I think that this was in section 7.8 if I've remembered the number correctly. And this is the exact same result, just with sequences instead of improper integrals. But maybe to motivate this a little bit more for you, we could have a think. So here we know that we care about, let's just take the first example here, part A. So here it's saying that we know something about some series bn, and we want to say something about the series an. So if I were to draw myself a little plot of, let's say, n against the nth partial sum. So we know that when we're thinking about sums of infinite series, we often think about the nth partial sum, right? Because it's easier to work with, as we saw 2 classes ago. So if I were to sketch out a little plot of what some bn might look like. So here we're saying that in our first case, remember, we had that bn must be convergent. So the nth partial sum of my bn might look something like this. So this is my nth partial sum of some bn. I'll write it as bi, so we don't have two n's in there. And we're saying that we know that this is convergent, so it tends to some limit. Let's call it L, say. And then the question is, what does knowing that tell me about an if I've got these two criteria here? So I know that my every single term in my sequence an has to be bigger than 0. So then I know that each of my nth partial sums has to get larger, right? My second partial sum must be bigger than my first. My third partial sum must be bigger than my second, because every time I'm adding on a positive quantity. So my nth partial sum for an must be getting bigger and bigger. But we also know that every single term in my sequence an has to be less than the term in bn. So the nth partial sum of a must be less than the nth partial sum of b. And what that tells me is that my sequence, my kind of nth partial sum for an must lie somewhere in this area here underneath the one for b, because it's definitely positive, but it's also lower than b. I'll just rub that out there so we keep things nice and neat. So essentially, my an can look anything like this. This is my nth partial sum of ai in this case, and it can lie anywhere in that region. And then the question is, now, does my sum, my infinite series an, converge or diverge? Well, we know that it's constantly increasing. I've just said that. It has to get bigger and bigger the bigger that we make n, or the upper limit. And we also know that it's bounded from below by 0 and bounded from above by the limit of bi, the L in my case here. And so by the, I'll write it here as the MST, that was our monotone sequence theorem. That implies that our infinite series AN is convergent also. Just to give you a little bit of, I've not really left myself enough room there, have I? There we go. Just to give you a little bit of motivation why that holds. And indeed, the exact same thing will hold for the divergent case. Here I'm saying I know that I've got some divergent series, AN, and BN is bigger than that divergent series, so BN must diverge also. And hopefully you remember that kind of reasoning that we did for the comparison theorem for improper integrals. Or indeed, if you just want to think of this as the kind of series version of that improper integrals test, then that's a perfectly kind of reasonable way of thinking about this too. As always, I think it's a little bit easier to see these kind of things through an example. So we'll carry on with this example here we were working on when we were thinking about the infinite series of 1 over n to the 4 plus en, and we were thinking about whether that was convergent or not. So you remember the point we got up to is that our guess was that this was indeed convergent. And this ties us back to the comparison theorem for improper integrals again. If you remember, the way we worked on that there was that we took our best guess as to whether our integral was convergent or divergent, and then accordingly we tried to find another convergent or divergent integral that was either bigger than it or smaller than it. And that's the exact thing we're trying to do here. So if we're in our guess that we've got a convergent series, we're in our case A situation. And my goal is going to be to find some Bn, which is larger than our series and also convergent. So I can summarize that here. That means we would need to find Bn, which is larger than or equal to An for all n. We also need Bn to be positive, bigger than 0 for all n. And we also need the sum of Bn to be convergent. So that's our kind of 3 requirements. And if I were to do a divergent type example, we'd have the same thing, but kind of all flipped around. Hopefully you can kind of have a think about what those cases would be. So I guess I have one kind of extra requirement that I haven't said, and that's that it would be a lot easier for me to work this out if I can find some Bn that has a known form, i.e. something I already know is convergent, but I don't need to kind of do any more work to show that it is. So in this case, I'm going to notice that the thing that we're trying to think about here is 1 over n to the 4 plus e to the n. And I think the first step to say here is that we can say that that quantity there must be strictly less than just 1 over e to the n, as long as we have n greater than or equal to 1, which is what we require here, right? We have the sum from n equals 1 to infinity, i.e. all n greater than or equal to 1. If you need a little bit more explanation as to why this is true, this is because I can note that e to the n must be strictly less than n to the 4 plus e to the n for all n greater than or equal to 1. This is because n to the 4 must be a quantitative quantity, so if I add it to e to the n, it has to make it larger. And then when I take the reciprocal of these values, I kind of swap the inequality over, and you can see that's what I've done here. So therefore, I've done my first kind of one of my 3 requirements, right? I found some new sequence, 1 over e to the n, which is bigger than my sequence an. Have I done my second requirement? So I said that I needed Bn to be greater than or equal to 0 for all n, and that's true here. So my 1 over e to the n, which I'm saying is going to be Bn here, is indeed positive for all n. This is always going to be a positive quantity, 1 over e squared, 1 over e cubed, and so on. And so my second requirement is also done. Now I've just got the last one to think about. Is my sequence Bn, my new series defined by Bn, convergent? I.e. what happens if I compare with the sum from n equals 1 to infinity of 1 over e to the n. And as always, I'm just going to write out a couple of terms to think what this looks like. I can see that that's going to look like 1 over e plus 1 over e squared plus 1 over e cubed, and so on until infinity. And the good thing I see here is that I've managed to find myself a geometric series. In particular, I note this, I can see that to go from one term to the other in my sequence, every time I'm multiplying by 1 over e. 1 over e to 1 over e squared to 1 over e cubed, and so on. And so I've got a geometric series with r, my common ratio, equal to that multiplicative factor, 1 over e, and with a, which we defined as the initial term in the sequence, and that's just 1 over e also actually, in this situation. Sorry about that. A equals 1 over e also here. And we already know that a geometric series converges as long as the absolute value of r is less than 1. And indeed we have that here. 1 over e, it's 1 over about 2.7. And so that's going to be less than 1. And so we have a convergent geometric series. Actually, we don't really need to know the value of the series, but we can work that out anyway. We remember that the sum of a geometric series with r less than 1 is given by a over 1 minus r. If you've not worked on memorizing that formula yet, it's a super important one and it comes up all the time. So I'd really recommend kind of getting that a minus 1 over r in your mind, put it on your post-it note, stick it on your desk until you remember it. And in that case, we can just sub a and r into that, and that gives us 1 over e divided by 1 minus 1 over e. Or to write that a little bit more simply, 1 over e minus 1. And just to make super clear, I'm just going to, I keep doing this zoom in, whoop. I'm just going to write, it converges once again. Okay, and then we need to kind of step out at our last step to kind of refer back. Let's kind of, I can zoom out to the whole page and everything, just to look at the whole question as a whole. So we've gone back, we've found our Bn that fits all of our requirements. In fact, I can tick the last one off my list now, right? I have all 3 requirements for my convergence test. I have my new sequence Bn bigger than An, I have my new sequence Bn bigger than 0, and I have a convergent series, the sum from n equals 1 up to infinity of Bn. And now I just need to do one little sentence to finish off the problem. So I know that my series Bn converges, so I can say that this implies that something smaller will converge also. And just to finish off, I can say therefore that the sum from I equals 1 to infinity of 1 over n to the 4 plus e to the n converges by the comparison test. So just to kind of demonstrate to us what you mean on these kind of questions, you know, in an exam situation or something like that, it doesn't hurt just to kind of try and lay things out and kind of prove to us that you understand all these requirements of the test, as I've kind of written out in this box over on in this area over on the right here. But also just to do this little sentence that summarizes it at the end, just to kind of finish things off. I think it kind of neatens it off a bit. And I've kind of alluded to this a little bit earlier, but the next tip over the page just kind of summarizes that when we're applying the comparison test, we often try and use geometric series or p-series for the comparison. And this is just because we know these results about convergence on those special kinds of series. So it kind of saves us a bit of work and always gives us something nice to compare to. So we'll carry on with a second example. And here we're asked to test this new series for convergence. And the new series is defined as the sum from n equals 1 to infinity of 1 over n factorial. And nicely in this case, we've already got a couple of the first terms written out for us. Or just to make it super clear what we're thinking about, we can see that the first term's going to be like 1 over 1 plus 1 over 2 plus 1 over 3 times 2 plus 1 over 4 times 3 times 2 and so on, up to n equals infinity. So we've just got the sums of the reciprocals of factorials here. And we're going to do those kind of same steps again. So first, the question is, like, what do we think is going on here? What would be our best guess? And again here, I'm going to guess convergence. I might be wrong. I might end up, finding that this sequence doesn't converge and I have to try out a different comparison test. But at least initially, this is going to be my kind of best guess of what's going on. The reason I say this is because n factorial is in the denominator. And also the fact that it grows very quickly. It meaning n factorial. So the more and more terms we get in our sequence, the bigger and bigger our denominator's getting, and so the limit of our terms is looking like it's going to be 0. And like we said in the previous case, that does suggest convergence. It is one thing that's necessary for convergence, but it's not sufficient, i.e. our harmonic series where we saw that didn't hold. So it suggests that I might be looking for convergence, but we're not yet kind of confirmed. Something that's kind of interesting, I'm just going to do a little step aside for this a minute, is that sometimes people aren't sure of the value of 0 factorial. And in fact, this is actually 1 by definition. I think sometimes people think that it should be 0, but actually we define it as 1. And interestingly enough, if I had given you the sum here from n equals 0 up to infinity of 1 over n factorial, the actual value of the sum, it will be different in our case because we don't have that 0th term. But if I had given you that, we would have found the value of this sum to be e. And actually I think that's pretty fascinating and a bit of a weird, why would a sum of 1 over n factorial be e? But this actually comes from the definition of e being the base of the natural logarithms. And actually this kind of correspondence here, that this sum is equal to e, was found out kind of before e was fully defined by the mathematician Bernoulli back in the 1600s. And this actually came out of calculations of compound interest in banks, how you end up getting paid interest on the interest and so on. So if you're kind of interested in these things, I'd recommend having a look at that up. But yeah, anyway, in our case, this series is going to have a different value because we don't have that first n equals 0 term. But we can kind of carry on anyway to try and think about whether this is converging or not. So one thing I want to note to test that, so I'm going to need to find something to compare to my sum from n equals 1 to infinity of 1 over n factorial. And we know that this is going to look like, just to fill in what the factorial looks like, the sum from n equals 1 to infinity of 1 over n times n minus 1 times n minus 2 times loads and loads of numbers until eventually we get multiplied by 1 there on the bottom. So all the numbers from n down to 1. And again, I'm going to be looking for, I think that this is converging. So I've got my same kind of criteria that we had in the previous example. I want some series Bn which is bigger than it, positive, and also convergent. So I need to think about something which bounds, which is bigger than essentially this expression I've got here on the right, my 1 over n plus n minus 1, n minus 2, etc. And to think about this, I'm going to note that my denominator here, my n times my n minus 1 times my n minus 2, and well, one thing we want to note first is that actually I can consider the factorial only going down to the value of 2. So you can imagine that in reality I actually have a 1 on the end there, but multiplying an equation by 1 doesn't change it at all, just means we multiply by 1, so I might as well not have it there in the first place. And this will be kind of key in just a second. And what I can notice is that my denominator must be strictly greater than or equal to this many, i.e. this many, 1, 2, 3, however many numbers I've got here, it must be less than, greater than that many 2's. So 2, I replace my n with a 2, I replace my n minus 1 with a 2, I replace my n minus 2 with a 2, and I replace every single term in this product with a 2. This is just because n is bigger than 2 and n minus 1 is bigger than 2. And so when I multiply these all together, my whole expression on the left must be greater than or equal to my whole expression on the right. And the question then is, how many of these 2's are there in this expression here? And this is where the 1 thing came in. There are going to be n minus 1, lots of 2 there on the right hand side. And just to kind of summarize that, this is because we had no number 1 here, right? So actually we had initially had n terms on the left, n multiplied by n minus 1 multiplied by n minus 2, but we said that multiplying by 1 didn't impact the left hand side, and so actually we've got n minus 1 lots of 2 or n minus 1 terms on the left, and so that's why we can say that n factorial must be greater than or equal to 2 to the n minus 1. But we remember that our initial expression, our series we're working with, isn't n factorial, it's 1 over n factorial. And so if I'm comparing 1 over n factorial, I have to inverse my inequality sign, and 1 over n factorial must be less than or equal to 1 over 2 to the n minus 1. And this was my kind of first criteria, right, in my comparison test. I've now found some new sequence, 1 over 2 to the n minus 1, which is bigger than my original sequence, 1 over n factorial, for every single n. My other question, so I guess let's just summarize that. I've now found some bn, which is greater than or equal to an. And I'll just give myself a little tick. The other question is, do I have bn greater than or equal to 0 for every n? And I believe that that does hold here for all n greater than 1, right? So this here on the right hand side, my bn is 1 over 2 or 1 over 2 squared or 1 over 2 to the 4. Any of those numbers are all going to be positive. So my second requirement is done. Then the last bit to work out, as before, is does my sum from n equals 1 up to infinity of bn, my 1 over 2 to the n minus 1, does that converge? And if I write out, as usual, a couple of my terms to check, so you can see that this series is going to look like 1 plus 1/2, 1 over 2 to the 1, plus 1 over 4, and so on. And again, we've ended up in a really nice place where this is a geometric series. And the more of these you kind of practice, the more you'll kind of be able to kind of identify, trying to find these geometric series or these P series, which bound the things you want to test. We notice indeed that this is a geometric series because when we go from one term to the other here, we're multiplying each time by a common ratio of 1/2. So 1 times 1/2 gives me 1/2, 1/2 times 1/2 gives me 1/4, and so on. So just to clarify, we've got r here equal to 1/2, which we know is less than 1, that we require for a geometric series to converge, and I've got a, my first term in the series, just being equal to 1. So again, we don't actually need to work out the value of the limit here of our geometric series. If we did, it would be a over 1 minus r, so 1 over 1 minus 1/2. But actually, it just suffices to say that because our common ratio is less than 1, our geometric series converges. So let's just sum up. I can say that the sum of 1 over 2 to the n minus 1 is a convergent geometric series. And therefore, the sum of n equals 1 up to infinity of my 1 over n factorial, so we're just doing our finishing off sentence, converges also by the comparison test as it is smaller, let's say. So just a little sentence to show that you know what's going on, that you understand which version of the comparison test we're using, just a good opportunity to kind of demonstrate your knowledge. So every time we do one of these questions, it's going to be the same kind of process, particularly if we're looking for testing for convergence. So first we do our guess. Do I think that my sequence is convergent or divergent? Looking back at the definition of the test, which of these cases A and B am I in? Once I've got that, I need to find some new sequence that satisfies the requirements. That we have Bn bigger than An, that we have both sequences Bn and An bigger than or equal to 0, and that our second sequence either converges or diverges as we require. So it's kind of a good process to kind of get into and have memorized. The final section of the course takes on another little test that we can learn, and this is on a similar theme. So the limitation of the comparison tests that we've seen so far is that sometimes it can be hard to find this second sequence, Bn or An, which has all the requirements that we need. Those three things: a sequence that is always positive, one that is strictly bigger than the other, and that it needs to converge or diverge. Sometimes that can be a little bit tricky. And in these cases, the limit comparison test can come in to help us. So this test is defined as follows. So here we're still going to assume that we have two series, the sum from n equals 1 to infinity of An and the sum from n equals 1 to infinity of Bn. And we do still require that these are both series with all positive terms. You can imagine if I had defined one of them as having always negative terms, then I could just kind of do a little rejig and take the negative of it. But just for the argument's sake here, we're going to say that they need to be both entirely positive terms. But that is the only requirement here. I can say here, note here, that we no longer require that other step we had in the previous one, i.e. we no longer require An less than or equal to Bn for all n. So it's a little bit more of a lax requirements that we have to satisfy here. And in this case, if I take my two sequences, An and Bn, and I divide one by the other, and I take then the limit of the resulting sequence as n tends to infinity, it turns out that if my answer, we call it C, say, if that C is a finite positive number, then either both of our series must converge or both of our series must diverge. So I'll just explain that a little bit more because I know that's a bit of a long introduction. So as long as we have our two series, both of which with positive terms, I can form a new series out of their ratio, this An over Bn quantity in here. Then if I take the limit as n tends to infinity of that new sequence, I might get infinity, in which case I can't use this comparison test. But if I get some answer C, which is both finite and positive, then we know that either both of the series converge or both of the series diverge. And the reason that this is useful is, let's say I've got some sequence A and I suspect it converges. Then if I find some B that I know converges, and I take this limit of the ratio of the two and I get something which is finite, then because B converges, I know that A must converge also. And the exact same thing for divergence. If I think that my An diverges, I pick a divergent B, I take the ratio, I take the limit, and if I get some finite positive C, then the fact that B diverges tells me that A must diverge also. So maybe a bit of a, there's a couple of different arguments there to try and think about, but let's try and do an example to convince ourselves of why this might be true. So here I'm going to do this example of the sum from n equals 1 up to infinity. So I know in these two examples here we haven't explicitly written n equals 1 up to infinity, but this is just a reminder that when those things aren't written on the limits here and here, we can just assume that they are indeed 1 up to infinity. That's the kind of standard kind of sum that we would have here, and we're thinking about the sum of 3n squared plus n over n to the 4 plus root n here. And the goal is going to be to find some positive Bn, which we already know either converges or diverges, depending on which one of these two, depending on what we kind of think about this equation that we're starting with. So the question is, as with the regular comparison test, do I think that my sum of 3n squared plus n over n to the 4 plus n converges or diverges? And what I'm going to think about here is, let's for argument's sake label this guy that we're starting with as our an. So an is 3n squared plus n over n to the 4 plus root n. In the definition of the limit comparison test, it doesn't really matter which ones are a and which ones are b, so for argument's sake we'll just say that this is our an. And then the question is, what bn do I need in order to do this comparison test? And to find this, my general advice is always going to be to consider the dominant terms in the numerator and the denominator of an. And by this I mean, when I take, eventually I'm going to be taking the limit as n tends to infinity of my an, my expression here. Which of the terms in this are going to be dominant at that case? So on the numerator we can see that that's going to be 3n squared, since 3n squared is bigger than n. And so on the top of my bn, I put that dominant term, 3n squared. In the numerator, sorry, the denominator of an, the dominant term as n tends to infinity is going to be this n to the 4. Because when n is really big, n to the 4 is much bigger than the square root of n. So I set that dominant term as the denominator in b. So I call my b 3n squared over n to the 4. And indeed we can see that that cancels out a little bit to give us 3 over n squared as my bn. And we'll see in a second why it's kind of helpful to think of bn this way. So now we're going to think about, and this is where it will kind of appear to us, we want to think about the limit as n tends to infinity of our an over our bn, just like it says we should do in our limit comparison test. And this is where defining b like this works things out for us nicely. So we can say that when we take that, I'm going to get my an expression, 3n squared plus n over n to the 4 plus root n, and I'm going to divide that by bn, i.e. divide it by 3 over n squared. And I can simplify that out, so I'm going to get the numerator of b, the denominator of b multiplied by the numerator in a. That's going to give me, let's not forget our limit as n tends to infinity here. When I multiply out those fractions, I'm going to get a 3n to the 4 plus n cubed on the top of my fraction, and on the bottom I'm going to get my original denominator, n to the 4 plus root n, multiplied by this 3 here in bn, or for argument's sake I could just write a 1/3 on the outside of my fraction. And now we know that we want to think about what value this limit is actually going to take. So the kind of normal approach when we're working out limits of polynomial expressions like n to the 4 and our n cubes and stuff here is that we divide through by the biggest power, right? Oh, sorry. So I can do that exact same thing here. I can say that this is exactly equal to the limit as n tends to infinity of my 1/3 multiplied by, well, if I divide through every single term by n to the 4, I'm going to get 3 plus 1 over n over 1 plus, this last term is going to be n to the 1/2 minus 4, which I believe is 1 over n to the 7 over 2. Now this is a quantity that I can actually think about the limit as n tends to infinity, so all my 1 over n's are my 1 to the over n to the 7 over 2. As n gets really big, those fractions are going to tend to 0, and indeed the limit of this is going to be my 1/3 on the outside times 3, i.e. the limit of my n as n tends to infinity of an over bn is 1. And this is exactly what we're hoping to find in these two expressions, right? We were trying to find some finite positive c as the answer to this expression, and that's exactly what we've got. So I can just summarize here. 1 is finite and positive, and so I can say, so by the limit comparison theorem, an and Bn, or I guess the sum of those two things, must either both converge or both diverge. And then the question is, well, I want to find out about my an, my sum of an, which was our sum of 3n squared plus n over n to the 4 plus root n. So does my sum of bn that I picked converge or diverge? So at this point, we should go back to the definition of it up the top of the page, and we see that it was 3 over n squared. Running out of room a little bit at the bottom here, but I can say we had, the sum of bn here was equal to, let's just factor out the 3 times the sum of 1 over n squared. And this is just a p-series, right? This looks like, well, 3 times a p-series at least. And so that must converge. If you had a little bit more room here, you could be taking up a little bit more space than me. So we know that our series, the sum of bn converges. And so my sum of an converges also. So I'll just sum that up a little bit more in words. We've found out all the requirements of our limit comparison test here, right? We have 2 positive sequences, the one we were given, 3n squared plus n over n to the 4 plus root n. I've also found another positive series, bn, given by 3 over n squared. And as it turns out, that series converges. Just separate that off a little bit. And because I found my limit as my n tends to infinity of an over bn, because that was a finite and positive value, I know that an and bn must either both converge or diverge, and then because bn converges, an converges also. So there's a lot of these kind of inference statements here. But I think that once you kind of get the hang of these convergence tests, it's kind of often applying the same steps, just kind of in new ways. So hopefully that's all clear, and I'll be back with section 11.5 shortly. Thanks very much.